During a rainstorm, any light source used to illuminate the scene will also reflect off of nearby raindrops. For example, the headlights of a car driving at night will not only brighten the road, but also brighten the drops, causing distracting flashes. In this paper, we present a method that uses high-speed adaptive projection to illuminate the scene, but not illuminate the drops. This will give the driver better visibility at a time when it is most needed. This illustration demonstrates our basic idea. The car's headlights illuminate the scene, and some light rays intersect drops. These illuminated drops will appear as bright, flickering, distracting streaks. However, if we can determine the rays that are illuminating only drops, we can momentarily turn them off. As the drops are moving quickly, each ray will spend only an imperceptible fraction of a second off, giving the driver the impression of headlights that see through rain. We capture images with either a stereo camera pair or a co-located camera projector system. Once the image is acquired, we quickly process the image to detect the particle and predict its future location when we are finally able to update the lighting to not illuminate it. Using simulation, we have investigated the requirements for such a system to be feasible. Here is a simulation of rain, 5 mm per hour, with a system latency of 13 milliseconds. Our adaptive projection system runs at 120 Hz. This first example is a simulation with a stationary camera. Black streaks are the drops successfully not illuminated. The red streaks at the top are drops that the system has not yet recognized. If we add forward velocity, the drops enter the field of view from the top and the sides, which makes the task challenging, though not impossible. At 30 km per hour, the accuracy is 73%. At very high speeds, our system is still capable of not illuminating many of the drops, while still maintaining high light throughput. We have also created a prototype camera projector system that detects drops and adaptively adjusts the illumination. The system consists of a co-located camera and projector, both running at 120 Hz. Based on the captured images, this prototype system adapts the projector lighting every 8 milliseconds. This video shows how the system operates on a single drop. The camera input is fed into our system, which predicts the future location of the drop and directs the projector to not illuminate it. For the predicted location video, the color red indicates the parts of the drop that are incorrectly illuminated. Green indicates the parts of the drop that are correctly not illuminated, and blue indicates pixels that were incorrectly turned off. This video shows multiple drops released from different drop emitters. The system is able to track and predict the future locations of each drop at 120 Hz. Shown here are drops falling at 32 drops per second, which is equivalent to a severe thunderstorm. The drops are falling against a background with varying brightness and contrast levels to simulate nighttime driving on a busy road. As can be seen, the visibility is much improved when the illumination is reactively controlled. Increasing the system's speed and performance will make adaptive headlights a real possibility, making driving in inclement weather safer and less stressful.